Hello and welcome to this video in which I will show you how both single indicator and multiple indicator latent growth curve models can be formulated within the hierarchical linear or multi-level modeling framework. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. On Tuesdays I usually talk about an analysis in the Mplus software, and on Thursdays I address more general issues in multivariate statistical analysis, including factor analysis, structural equation modeling, multi-level analysis, and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including a link to my free weekly statistics newsletter, as well as free courses that I offer through QuantFish. In this video, I want to show you how both univariate or single indicator growth curve models and multivariate or multiple indicator growth curve models can be formulated as multi-level models, and I will focus in my presentation on a conceptual representation of these models using path diagrams rather than equations, so that you can hopefully, even if you're not that familiar with the mathematics behind these models, you can understand how this works and when this may be useful for you. So I'm going to start with a univariate or single indicator linear latent growth curve model that you can see here in this path diagram, specified as a regular longitudinal confirmatory factor analysis model, where we have an observed score at each time point, in this case 4 time points or 4 measurement occasions. For example, those could represent repeatedly measured anxiety scores on 4 measurement occasions, and we're trying to find out whether there's any change over time, and we're specifically analyzing linear change here with a linear slope factor, which is depicted here on the right hand side. And so this model allows us then to model linear trajectories in anxiety across time. We can describe this model with a single measurement equation in the confirmatory factor analysis framework, where we have a time-specific outcome variable yt, which represents our measured anxiety scores, and that variable is dependent on an intercept factor that represents the true anxiety scores at time 1. So it's like a true score variable for y1, and then plus we have a slope factor in our equation which affects all variables except the variable at time 1, and it represents linear growth because the loadings here are fixed according to t minus 1, so a loading of 1 for time point 2, a loading of 2 for time point 3, a loading of 3 for time point 4, assuming that the measurement occasions here are all equally spaced. And then finally we have a measurement error variable epsilon t here, which comprises measurement error and time-specific variance that is not reflected in the growth factors. So now, how can a model like this be specified as a multi-level or hierarchical linear model? The idea is that this is basically a regression equation with random coefficients, so it can be represented as a random coefficient regression where the intercept is a random coefficient that varies across individuals, and the slope is a random coefficient that varies across individuals. And so, since longitudinal data has a multi-level data structure with time points nested within observations, we can estimate the parameters of such a growth curve model also within the framework of hierarchical linear modeling or multi-level modeling using random coefficient regression analysis. And that's what I want to show you next. So when we represent this exact same model as a multi-level model, then we have 2 different levels. Level 1 is the level of the measurement occasions, and in the multi-level modeling framework we would have only 1 column to represent our repeatedly measured anxiety scores, because multi-level data comes in long format, or is typically represented in long format for multi-level analysis, whereas when we estimate a confirmatory factor analysis based growth curve model, then we use wide format data, where we have 1 column for each time point, therefore a wide data set. Now those 4 columns are stacked into 1 column, so we have long format data set, and we have a person ID variable that tells us say which rows belong to which person. We have a time variable that tells us which time point we're looking at, and so the data are organized in a different format, so-called long format, and therefore there's only one outcome variable here at level 1, rather than having 4 variables, one for each time point. And so now in the level 1 model, we have the time variable, which is a level 1 predictor variable, so that varies, so say at level 1 where we have time point 0, 1, 2, 3, and this variable predicts our outcome variable y with random coefficients, which in the notation that, for example, the Mplus folks use for the Mplus structural equation and multi-level software in their documentation, in that notation the random intercept of that regression is indicated with a dot on the border or on the edge of the outcome variable here. So this dot represents a random intercept coefficient of this level 1 random coefficient regression, and then also there's a dot on the arrow that points from time to y, indicating a random slope. So those two dots indicate that the coefficients of that level 1 regression are random coefficients, meaning they have variation between people at level 2, so we'll estimate a variance for each of these variables at level 2. They will be treated as latent variables with variation across or between persons. And then furthermore, there is a residual of this level 1 random coefficient regression that represents again measurement error and time-specific influences. So that corresponds to the epsilon t variable in the confirmatory factor analysis specification. At level 2, we are then modeling the intercept and slope coefficients, the random coefficients of the level 1 regression, as latent variables. So they have as a parameter, they have a mean and a variance and a covariance that are estimated as level 2 parameters in an unconditional model. In a conditional model at level 2, you could have predictor variables. So for example, you could have gender at level 2 predicting the intercept and slope to find out whether there are any differences between males and females on the initial anxiety level and or in terms of the rate of change across time. So then there would be a conditional model where you could have level 2 equations in which you could regress the intercept factor and or the slope factor on level 2 predictor variables such as gender, for example. So in summary, we estimate in this model specified as a multi-level model at level 1 only the variance of epsilon, and of importance within this framework, the implicit idea is that the variance of epsilon is set equal across time. So there's only one parameter, and so that implies that the variance of epsilon is constant across time, which is not the case when you estimate this model in the confirmatory factor analysis framework, where we typically would estimate a separate error variance for each time point. So that's one difference, although those models are conceptually the same, and they would be the same if you had balanced data and if you set the error variances equal within the confirmatory factor analysis specification, you would obtain the exact same parameter estimates. However, if you leave the error variances free in a confirmatory factor model and you use the multi-level specification, then you will not get the same results between the two, because there's this constraint here on equal error variances. At level 2, we're estimating the mean and the variance of the intercept and slope factors here, and also the covariance between intercept and slope. So this should say variance intercept, and here we have then the mean of the intercept as well as its variance, and here we have the mean of the slope and the variance of the slope and the covariance as parameters. If we had predictors at level 2, then there would be other parameters such as the regression coefficients from that predictor to those intercept and slope factors, and we would estimate residual variances for the intercept and slope as well as potentially a residual covariance between them. So that's what this looks like for a univariate growth curve model, a single indicator growth curve model specified as a multi-level random coefficient regression model. Now let's take a look at a multiple indicator growth curve model, which can also be specified in either the CFA framework, the single level CFA framework, or the multi-level modeling framework. With a multiple indicator design, we have more than one outcome variable at each time point. So for example, 3 different anxiety scales or 3 different items for measuring anxiety at each time point. So here Y11, Y21, and Y31 indicate 3 different indicators of anxiety at time 1, and then Y12, Y22, and Y32 indicate the same indicators measured again at time point 2. And then again, we have the same indicators at time point 3 and time point 4. So this is a multivariate design or a multiple indicator design where we have multiple outcome variables. Now this has an advantage over a univariate or single indicator growth curve model in many different ways, because this allows us now to properly separate time-specific or situation-specific variance from random measurement error, which is not possible in a univariate design. And also this can have more power for detecting inter-individual differences in change across time, as well as allows us to model indicator-specific growth factors so that we can see whether there are differences between indicators in terms of how sensitive they are to changes across time. So here I'm presenting a very general growth curve model for multiple indicator data that uses indicator-specific growth factors. And in this indicator-specific growth model, specified as a regular single-level CFA model, we would have a separate intercept and slope factor for each indicator. For example, for the first indicator, there is one intercept factor, intercept 1, and there's a slope factor, slope 1. And then there's one for the second indicator and one for the third indicator, and so on. So each indicator has its own intercept and slope factor, and they need not all be linear slope factors as well. So there could be some indicators that show non-linear trajectories where you leave maybe the loadings free, or you estimate an additional quadratic component or something like that. So it has great flexibility in terms of modeling differences between the indicators in terms of both the onset and the rate of change across time. All those factors can be correlated because they will be related, because they're all supposed to be measuring anxiety and or changes in anxiety across time. So there's a correlation allowed between these. And then in addition, we have time-specific residual factors zeta t, which account for situation-specific variance in anxiety. So for example, there could be deviations from the general growth pattern that are due to a specific situation at time point 1, 2, 3, or 4. And in a single indicator growth curve model, such reliable but situation-specific effects would be confounded with measurement error and would be all lumped together in the epsilon variables, whereas here they can be separated because we have multiple indicators, and so we can assume that they share the same situation-specific variation. And so we have epsilon then in addition to the zeta factors for each indicator. So epsilon 1, 1, epsilon 2, 1, epsilon 3, 1, and so on. They're just not all depicted here to avoid overloading this picture with information, but there is an epsilon variable included in this model for each of those YIT variables. You can also have a different structure in a multiple indicator growth curve model. One common way to specify a growth model with multiple indicators is by using a so-called second order growth curve models. That's a model that's related to this model, but this model here is more general because it allows each indicator to have its own indicator specific growth factor, and so it has greater flexibility in modeling differences between indicators in terms of the growth trajectories. But what I tell you here applies also to other types of multiple indicator growth curve models. Now let's take a look at how this multiple indicator growth curve model can be set up as a multi-level model. And so a difference here relative to the univariate model is that now we have multiple indicators at each time point. So a univariate random coefficient regression model will no longer be sufficient. There's more than one outcome variable at level 1, and therefore we need multi-level confirmatory factor analysis to estimate the parameters of a multiple indicator growth curve model. Let's take a look at how that turns out in terms of a path diagram. So now at level 1 we have 3 outcome variables. Again, all the scores for multiple time points for a given indicator are stacked into one column. So we have one column for the first indicator of anxiety, we have one column for the second indicator of anxiety, and we have one column for the third indicator. And so again, this comes in long format now rather than in wide format as for the regular single level specification that we just looked at. So there's only 3 columns for the outcome, and there's a column for the time variable again, and that's the exact same thing as in the single indicator case. So the time variable is again our level 1 predictor, and now we have 3 regressions. So it's a multivariate random coefficient regression model because each of these indicators is regressed on time with a random intercept. So we have 3 random intercepts now, and also with a random slope. So we have 3 slopes now. And we have the time-specific variable zeta because we want to model situation-specific effects that are shared between these indicators at the same time point, and that's reflected by zeta. And so that's why we need multi-level confirmatory factor analysis to estimate the parameters of this model, because there are now latent factors at both level 1 and level 2. And so we have multi-level factor analysis with factors at both levels. The zeta factor is a level 1 factor because it is time specific. And so here we estimate the loadings, delta for the zeta factor. The first loading is fixed as it would be in a single level CFA for identification purposes. And then we have also the epsilon variables at level 1, 1 for each outcome variable. So there's epsilon 1, epsilon 2, and epsilon 3. At level 2, we again have our intercept and slope factors that are based on the random coefficient regressions of the level 1 regression on time. And so these factors again can all be correlated as in the standard single level CFA representation of this model, and we estimate the relevant parameters for these. Now at level 1 we have as parameters, in addition to the factor loadings delta, we have the variance of zeta that is estimated, and we have 3 error variances, 1 for each indicator. At level 2 we estimate all the parameters that we would also estimate in a single level CFA specification of this model. The means of the intercept and slope factors, the variances of the intercept and slope factors, as well as their covariances are estimated as level 2 parameters. So this is how this model would look like as a multi-level confirmatory factor analysis model. It can be estimated in all structural equation modeling software packages that can handle multi-level confirmatory factor analysis. For example, in Mplus you can specify this model. You can also specify the univariate model as a random coefficient model in Mplus. You can use LAVAAN in R for estimating a multi-level CFA, and other SEM software packages will allow you to do that as well. Now, what advantage does it have to use the multi-level specification rather than the regular single-level confirmatory factor analysis specification for estimating growth curve models? One advantage is when you have many time points and when the time points are imbalanced, meaning the distances vary within individuals and or between individuals. You maybe have a lot of missing data, meaning you have some individuals who contribute only 2 or 3 time points, other individuals contribute 10 time points. And so when you have a vastly imbalanced design, then the confirmatory or single level confirmatory factor analysis specification becomes very tedious and complicated, because you need a separate column for each time point, and then you have lots of missing values in there when it's imbalanced, and then also when the time points are variable and not balanced, then it becomes complicated. And so in that situation the multi-level approach can be useful, because everything is just simply stacked into one column. You have a time variable that can give you the exact time in continuous metric, and so then it becomes easier to specify a model like this. as a multi-level model rather than a confirmatory factor model at a single level. I hope you found this video useful. Please also check out my other videos on how to run growth curve models and growth curve models as multi-level models in the Mplus software. You find more videos on this topic here on this channel. Don't forget to subscribe to this channel and to check out the description for additional free workshops, including workshops on Introduction to LAVAAN and Mplus, and I'll see you next time.